Hello everyone, myself Purva Joshi, Assistant Professor at LJ Institute of Engineering and Technology. Today we are going to discuss few examples of partial derivatives. So let's begin with the higher order partial derivatives. Partial derivatives of higher order of function u is equals to f of xy are obtained by partial differentiation of first order partial derivatives. If u is equals to f of xy, then uxx, that is del square u by del x square, is equals to del by del x of del u by del x, right? Then uyy, that is del square u by del y square, and this is del by del y of del u by del y. Okay, then uxy means del square u by del x del y. Okay, so this is del by del x of del u by del y, and uyx is equals to del square u by del y del x, that is del by del y of del u by del x. Okay, so means if u is equals to f of xy is given, so firstly we have to find this del u by del x and del u by del y. Okay, del u by del x means what? Differentiation of u partially with respect to x, and we have to keep y as a constant, right? Del u by del y means what? Differentiation of u with respect to y, and we have to keep x as a constant. Okay, next, to find uxx, just apply this partial derivative with respect to x to del u by del x. To find u by y, we have to apply partial derivative with respect to y to this del u by del y, and to find uxy, we have to apply partial derivative with respect to x to this del u by del y, and to find uyx, we have to apply this partial derivative with respect to y to this del u by del x. Okay, so now let's begin with the example. If u is equals to function given, that is e raised to x plus y plus z upon e raised to x plus e raised to y plus e raised to z, and we have to show that this del u by del x plus del u by del y plus del u by del z is equals to 2u, right? So let's begin with del u by del x. Means we have to find the derivative of u partially with respect to x, and we will keep this y and z as a constant. Okay, so for that we will apply division, right? So this denominator as it is, means e raised to x plus e raised to y plus e raised to z as it is. Derivative of numerator, it will give you e raised to x plus y plus z, and again derivative of this x plus y plus z will give you 1, because derivative of x is 1 and y and z are constant, so its derivative is 0, right? Minus, now numerator as it is, means e raised to x plus y plus z as it is, and derivative of denominator, so it is just e raised to x. Okay, and upon denominator square, that is e raised to x plus e raised to y plus e raised to z whole square, right? Now just take this e raised to x plus y plus z common. Okay, so what you will get? E raised to x plus y plus z common. So here we have e raised to x plus e raised to y plus e raised to z minus e raised to x upon e raised to x plus e raised to y plus e raised to z whole square, right? This will get cancelled. So what remains is this e raised to y plus e raised to z into e raised to x plus y plus z upon e raised to x plus e raised to y plus e raised to z whole square. Okay, here we have taken derivative with respect to x, so we are getting this answer. So similarly we can find del u by del y and del u by del z also. Okay, so you will get del u by del y as del u by del y as this denominator will remain same, that is e raised to x plus e raised to y plus e raised to z whole square, right? And here what you will get? E raised to, Here we are taking derivative with respect to y, so that y term will get cancelled. So here we have e raised to x plus e raised to z, and here e raised to x plus y plus z. Okay. Now similarly we can write del u by del z. So it will be e raised to x plus e raised to y into e raised to x plus y plus z upon e raised to x plus e raised to y plus e raised to z whole square. Okay, now we have to add them, that is del u by del x plus del u by del y plus del u by del z. Now you can see the denominator is same in all the three terms. Okay, so we will write this common denominator. Okay, and from the numerator we will take this e raised to x plus y plus z common. So here e raised to x plus y plus z is taken common. Okay, now you can see we have 2 times e raised to x, we have 2 times e raised to y, and 2 times e raised to z. Okay, so also we will take 2 common, and here we have e raised to x plus e raised to y plus e raised to z. Right, it this e raised to x plus e raised to y plus e raised to z will get cancelled, and what remains is 2 e raised to x plus y plus z upon e raised to x plus e raised to y plus e raised to z. Okay, now you know this is our function u. Okay, so we can write this as 2u. Clear? So this is what we want to prove. Okay, now let's begin with the next topic, that is mixed derivative theorem, or you can say Clairaut's theorem. Okay, so here the statement is, if u of f of x comma y possesses continuous second order partial derivatives, that is del square u upon del x del y and del square u upon del y del x, then this del square u upon del x del y is equals to del square u upon del y del x. Okay, this is our Clairaut's theorem which we have already studied. Okay, so the next question is, if z is equal to x cube y plus e raised to x y square, then we have to prove that del square z by del x del y is equals to del square z by del y del x. Okay, so here we have to prove this Clairaut's theorem. Okay, now firstly we will find this del z by del x. Okay, so partial derivative of z with respect to x. Okay, and we will keep y as a constant. So this y is constant, means as it is, derivative of x cube is what? 3x square. So 3x square y plus, now derivative of e raised to xy square. So it is e raised to xy square into, we will apply the chain rule. So you will get here y square, because derivative of x is 1 and y square is constant. Okay, now we will find this del z by del y, means partial derivative of z with respect to y, and we will keep x as a constant. So derivative of y is 1, so we have only x cube plus e raised to xy square into, now x is constant and derivative of y square is 2y, so you will get 2xy. Okay, now we will find this del square z by del x del y, right? So this you can write as del by del x of del z by del y. Okay, so we have to find the partial derivative of this del z by del y with respect to x. Okay, and we will keep y as a constant. So this is your del z by del y. So differentiate this with respect to x. So from this you will get 3x square plus, from this 2 and y are constant, so we will keep outside, right? And we will apply this UV rule for e raised to xy square and x. So firstly keep this e raised to xy square as it is, and derivative of x is 1, plus x as it is, and derivative of e raised to xy square is e raised to xy square into y square, right? Now simplify this, so you will get 3x square plus, take this e raised to xy square common, so you will get 2y e raised to xy square into 1 plus xy square, right? Now we will find this del square z by del y del x. Okay, so for that you have to write like this. Means we will find the partial derivative of this del z by del x with respect to y, and we will keep x as a constant. So we will differentiate this term partially with respect to y, right? So x is constant means 3x square as it is. So 3x square as it is, right? And the derivative of y is 1 plus. Now we have y in both the terms. So we have to apply this UV rule, okay? So this e raised to xy square as it is. Derivative of y square is 2y plus y square as it is, and derivative of e raised to xy square is what? E raised to xy square into 2xy, because we are differentiating it with respect to y. Okay, now simplify this, so you will get 3x square plus, take 2y common and e raised to xy square common from these two terms. So 2y e raised to xy square. Now here we have 1 plus this y2, and this term is out. So we have only xy square, right? So from this you can say that both the terms are same, right? So we can say that this del square z by del x del y is equals to del square z by del y del x. Okay, so I hope you have understood. Thank you for watching.